Well, good afternoon, everyone, and welcome to our ongoing live astronomy series. I am Justin Bartel, one of the astronomers at the Science Museum of Virginia. Happy once again to be your guide in the cosmos. If you're just joining us for the first time, welcome. Glad to have you here. We are trying to get to the edge of the universe, but we're going one small step at a time. So we're not going to see everything today. In fact, today we are still in the solar system. Our number one focus today is going to be asteroids, some of the smaller objects out there. Maybe not a topic that gets a whole lot of attention, but I think we've got another jam-packed and pretty fun show. A couple of announcements before we get started. As always, need to thank Allianz Partners, our sponsor for this series. Happy to have them on board as well. During the show, we'll be using the same software that we use in the Dome Theater at the museum. It's called Digistar 6, and through a lot of the show, I'll be watching right along with you. I've got it set up on a second monitor off to the side, so you may not see me looking at the camera all the time if you keep an eye on me, but that's just because I'm trying to enjoy the visuals as well. In fact, I'm going to get you switched over here so that you can see it too. And as always, I'm going to kind of look back briefly before we get going with this week's topic. We had a few questions last week, and man, maybe y'all fell asleep halfway through. I know it got a little bit long, but space is really big. We saw all four gas giants last week, but had some lingering questions in the comments about Saturn, kind of the midpoint of last week's show. So let's address a couple of those real quick. As always, if you've got questions or comments today, feel free to leave those in the comments. I'll try and get a couple of them during the show for you, but hey, maybe you'll star on next week's show. So let's jump back to Saturn. And let's take a look at a couple of interesting questions. The first one I want to return to is a question that was submitted by Jason. And Jason said, is Saturn bigger than the other planets? Well, Jason, I think I probably said out loud once that that Jupiter was the largest planet. And in fact, I can kind of show it to you here. If we add all the planets to the screen, we'll back away just a little bit so you can see them all. We've got Saturn and all of the other planets that are smaller than Saturn on one side, and then Jupiter off to the left there. In fact, Jupiter is large enough that if you took the other 7 major planets, squished them together into one big ball, Jupiter would still be bigger. It's more massive than the other 7 planets combined. Speaking of smashing things together, let's see. Next question is from Hudson, who asked, if you combined all of Saturn's moons, how big would that be? Hudson, I'm glad you asked. How could I not answer that question? So here are some of the moons I showed you last week. We've got our moon on the left. I showed you 7 of Saturn's largest moons last week, but I've put its top 9 on the screen for you. I'm going to replace our moon with Ganymede for a reason you'll see in a second. Now, if Titan, Saturn's largest moon, just gobbled up all of the other moons orbiting Saturn, there are 81 others plus Titan. It would add a little bit of size to Titan, but it's already the second largest moon in the entire solar system, second only to Ganymede. And the mass from those other moons, all the rock and ice that you'd add on to Titan, it wouldn't be enough to give it more mass than Ganymede has. It would surely grow in size a little bit, but it would still be the second largest moon in the solar system. So it'd look something kind of like that. While we're on the subject of moons, let's see, Ariana asked if, or she said, I remember seeing that Saturn has many moons interspersed between its rings. Is that correct? And do they keep the rings in place? Well, answer 1, yes. Certainly some moons interspersed in the rings here. I'm going to highlight the orbits of some of the closer moons to make them a little bit easier to see. And as we zoom in here, hopefully you can pick out a few of the orbits that are right among the rings there. Now, the moons don't so much keep the rings in place, but they do give the rings a lot of their structure. You see gaps in the rings, and in fact, some of the moons are orbiting in those gaps. So the rings give them structure, or the moons give the rings structure that way. And then you see even some finer little ridges and gaps in the rings. Some of those are just because of the gravity of moons farther out. So it almost looks like Saturn's rings are grooved like a record, for those of you watching that know what records are. And it's because of the gravity of all the moons here in orbit around Saturn. But the rings aren't staying in place. I showed you the final orbits of the Cassini mission last week. And when it was passing between Saturn's cloud tops and its rings, it also detected something called ring rain. So the little particles in the ring actually raining down into the atmosphere of Saturn. There's a chance that the rings disappear in a few 100 million years. So we get to enjoy them for now, but although the moon's giving them structure, not making them permanent. One other comment I wanted to address, this one comes from Jennifer, says, surprisingly, Saturn would float in a bathtub. Now that's not really a question, I know, but I'm going to make it a question by asking, would it? Yes, Saturn's density, on average, is lower than water's. So if you threw something with a lower density than water in water, it should float. But remember, the inside of these gas giant planets are not made of the same kind of stuff. They're broken up into different layers, or as we say in astronomy, they are differentiated. So you've got an outer layer that is gas, you've got some fluids and metallic hydrogen, and then a solid core that might be rocks, minerals, metals, stuff like that. So if first you found a large enough bathtub, which might also be a physical impossibility, and you threw Saturn in water, what would end up happening is it would at first kind of try to float there, but then the gaseous outer layers would be pulled away, and maybe the liquid layers of Saturn would kind of mix in with the water that you're throwing it in, and then that solid core would sink to the bottom. To take it to an extreme, imagine having a bowling ball, wrapping it in tons and tons of cotton candy. You might have a density, on average, lower than water, but you throw it in the ocean, it's not going to sink. So, fascinating fact about Saturn there, but yeah, some pretty interesting physics going on there for sure. I could probably do a whole other show about it, but I did have a whole separate show planned for you today. So let's get on to today's topics. Back here at Earth, should probably ask if anybody was able to watch the rocket launch over the weekend. Pitched it to you in the show last week, I believe. Perhaps one of the biggest space events of the weekend. The SpaceX Crew Dragon spacecraft carried astronauts into Earth orbit from Kennedy Space Center for the first time. First time astronauts have launched from Florida in almost a decade. About 19 hours later, they docked with the International Space Station. So astronauts Bob Behnken and Doug Hurley are up there now working on the space station. But one of the most interesting parts of the mission to me is this flag. This flag was carried to the International Space Station by the crew of STS-135. That was the final space shuttle mission in 2011. The same flag had also been carried on the first space shuttle mission, STS-1, back in 1981. Now, when the STS-135 crew left it on the station, they said that it should only be taken, should only be removed from the space station by other astronauts launching from Kennedy Space Center. Now, at the time, they didn't really expect the delay to be so long. There was a program on the books that was supposed to take over, have astronauts flying again in a couple of years after the space shuttle was retired. But it turns out there were some problems with that replacement program. It was way over budget, running really behind, and it eventually got replaced. Somebody made the difficult decision to replace a program that wasn't working, and now we have the commercial crew and cargo programs. So they're doing a pretty good job. We've got crew flying today, and they have now retrieved that flag after a 9-year wait. So I think that's pretty cool. Another really neat thing about the mission is seen in this shot. This is from a little downlink, a little video show that the crew did shortly after launch. That is, I believe that's Bob Behnken. It's kind of fuzzy, hard to see. But then in front of him was a stuffed dinosaur. It was actually a toy of one of their sons. Their two sons got together, got all their dinosaur toys together, and picked one that would fly with their dads into space. So I thought that was pretty cool. And speaking of dinosaurs, let's get on to today's topic. Asteroids. Those two topics certainly linked. But today, you probably don't hear a whole lot about asteroids unless one is getting really close to the Earth. And I guess, lucky enough for me, there is one in the news today. You've probably seen it all over Facebook or Twitter or whatever. Some asteroid going to zoom past the Earth. On Saturday, the one that's approaching is going to be some 3 million miles away, so not much of a concern. That is, 12 times farther away than the moon or something, so there's the moon's orbit there. And it's not an uncommon thing. We have asteroids get closer than the moon all the time. Here's the path of an asteroid called 2020 HS7 that flew by at the very end of April. And then in red, I've added the path of another asteroid, 2020 JJ, that flew by about a week later. That was on May 4th. I believe. Both of these got much closer to the Earth than the moon is. I'll try and fly in and rotate around so you can get a sense of just how close they were. Both of these asteroids were pretty small. If either of them had hit the Earth, we would have been fine. They're small enough that they would burn up almost entirely in Earth's atmosphere. They'd make a good light show for us, but only tiny pieces would make it to the surface of the Earth, if any did at all. These close flybys are a good reminder that we should keep an eye on these little rocks. After all, the dinosaurs are certainly a decent example of why these rocks are important. But what I want to try and show you today is that they also have interesting things to show us about how the solar system works. So we'll get there. First, a quick note about naming these things. I've rattled off a couple of weird license plate numbers, and this is just how astronomers designate these objects when they're first found. The first one, for example, that I want to talk about is the one that followed that red path. It's currently designated 2020 JJ. The number out front is a year. That's easy enough. The first letter is the part of the year the asteroid was discovered in. And then the second letter is the order in which that asteroid was discovered within that time period. So 2020 JJ, the 9th asteroid found in early May this year. 2020 HS7, that kind of name is a little more complicated. There's another character at the end. You may see it written as a large number or numbers at times, but it's technically a little subscript number. You decode it the same way, though, with one slight change. The second letter S would be number 18, but because there is a 7 there, instead of this being the 18th asteroid found in that time period, you have to go through the alphabet 7 times. We count up to 25 each time, so you find that this is 25 times 7 plus 18, which is, yeah, you're right, 193. So this was the 193rd asteroid found in the second half of April this year. Now, if you really dig into these asteroid designations, you will find that sometimes astronomers have to tack on a 3-digit number at the end. So let's see, a few hundred times through the alphabet. Now we're talking about thousands of asteroids discovered in just 2 weeks. And that's really how we've gotten up to nearly 1 million asteroids. They're known to exist in the solar system, probably millions of them altogether. But not all of them have those alphanumeric code names. About 23,000 of them do have regular names. And of course, there are rules for naming things like this. Those rules come from the International Astronomical Union. I think they made an appearance in last week's show. I'm just going to call them the IAU for short. Now, they have a lot of rules, and that's really what they do. They make rules for astronomers to help everybody communicate around the world. And the rules for naming asteroids include things like you need to be able to pronounce the name, can't be random characters. It needs to be non-offensive, non-political, non-commercial. They prefer one word. They prefer that it not break any rules like this one does. The name I'm highlighting there is Mr. Spock, and you're probably thinking, Mr. Spock? Well, what's the big deal? It's just that Vulcan guy from Star Trek, right? No, the astronomer that found this asteroid, and it's the discoverers that get to name these objects. It was Dr. James Gibson. He found Mr. Spock in 1971, and this was after a few years in his career, and he had to move around. He ended up in Argentina doing this work, and one of his constant companions on his travels had been his pet cat. His pet cat was named Mr. Spock because the cat was imperturbable, logical, intelligent, and had pointed ears, just like our Vulcan friend here. So it was the cat that was named after Mr. Spock, the character, and it was the asteroid that was named after the cat. And for some reason, the IAU didn't like that very much. And so now there is a rule on the books that says you cannot name an asteroid after your pet. I don't know. It doesn't make a whole lot of sense to me. But it wasn't always so complicated. There weren't always so many rules. The IAU is only 100 years old, and the story of asteroids goes back over 200 years. So we're going to go back to the beginning of that story and highlight the character immortalized in the name of that asteroid there, Piazzi, Giuseppe Piazzi. But he doesn't just appear on the scene without any context. So let's take a look here. This is the solar system as we knew it in the late 1700s. We knew of the planets out to Saturn, and astronomers were starting to make some pretty interesting observations about the planets they had found so far. For example, some mathematicians figured out that there appeared to be a mathematical relationship that described how these orbits were spaced out around the sun. You might hear it called Bode's Law sometimes, or maybe it's a more accurate name, the Titius-Bode Law. It just predicts how far these planets should be from the sun. And I'll show you what their predictions look like. So these dashed circles are where the Titius-Bode's Law predicts that the planet should be. So we've got Mercury in there. All right, not a perfect circle, but pretty close. We've got Venus, Earth, almost perfect matches. We've got Mars, again, like Mercury, pretty close on average. Something seems to be missing beyond Mars, but then the orbit of Jupiter, pretty close to the prediction. The orbit of Saturn, pretty close to the prediction. Then, in 1781, the planet Uranus is discovered. And perhaps surprisingly, it is almost a perfect match for the Titius-Bode prediction as well. So that really makes astronomers pause and think for a second about what's going on between Mars and Jupiter. Why does this mathematical relationship predict that a planet will exist when we can't find one? So astronomers decided to try and answer that question. So a group of astronomers got together and they decided to break up the sky into different pieces and patrol that sky as a group that they called the Celestial Police. Now, it's kind of a strange name to pick, especially because the first modern police force wasn't started until London in, 1829. And these astronomers, 24 of them, were from all over Europe, where the practice of policing took all different forms. But in a lot of places, it was still just kind of voluntary or informal night watches. And that's really what these astronomers were looking to do, was just watch the sky and see if they could figure out what was going on up there, why it looked like a planet was missing from our solar system. So they were getting organized in the year 1800, but on January 1st, 1801, this astronomer, who was going to be invited to join, but hadn't gotten the invitation yet, while cataloging stars in the constellation Taurus, found something that seemed to match the description of what these astronomers were looking for. That's the object that we call Ceres today. And today, technically classified as a dwarf planet, but it was, at the time, considered the first asteroid discovered. But it wasn't instant agreement. Stop me if you've heard this story before. Astronomers find an object where they think a planet should be found, but it looks a little bit smaller in their telescopes than they originally expected. They argue a lot about whether they should call it a planet or not. And in the meantime, astronomers find even more objects that are in the same part of the solar system. Some of those other astronomers that were going to be part of the Celestial Police found three more, Juno, Pallas, and Vesta. And after a brief pause in the mid-1800s, astronomers started finding more and more and more more of these objects. That's part of the reason why they eventually settled on the name asteroids for these little worlds. There were a lot of them, and through telescopes, because they were so small and relatively far away, they looked kind of like stars. Asteroid just means star-like, so that's how they got their name. Now, as more and more discoveries piled up, astronomers started noticing some kind of unusual asteroids. I like that orbit in blue there. That is Eros. It's the first known near-Earth asteroid. It gets pretty close to our planet. We know of thousands of those today. That one was found in 1898. And then a few years later, 1906, another kind of strange one is found. It's on an orbit that nearly matches Jupiter's. It orbits the sun in the same amount of time. It keeps its distance from Jupiter all the time. Turned out to be the first example of thousands of Trojan asteroids, which pretty interesting collection. We'll take another look. And then a few years after that, 1920, Hidalgo is discovered. That one comes out near the orbit of Jupiter, actually crosses Jupiter's orbit, but goes a little farther away. Turned out it was the first example of something called a centaur. We found many more, but astronomers didn't really catch on to their existence until 1977, when another one was discovered. What you're watching is a replay of the discovery of the first 5,000 asteroids in the solar system. And it took until August of 1991 to find this first set of 5,000 asteroids. That's 190 years. So if it takes 190 years to get to 5,000, how do we have almost 1 million today? Well, in the 1990s, astronomers started doing something that, a lot of us started doing. They started using digital cameras. They were using photographic plates until that time. And with the digital detectors, you could search large parts of the sky and easily process the images with computers, allow you to make discoveries a little bit faster. It made it easier to pick up on smaller objects that might be moving faster through the sky as well. So with the introduction of digital detectors, we've been able to greatly increase the rate at which we discover asteroids, and we've also been able to find them farther and farther away. So if I add to our current map a representative sample of all of the objects known to exist in the solar system today, your entire screen pretty much turns green. These little worlds are all over the place. So it's not just the 8 big planets in the solar system. We have a lot of little worlds out there too. Now you can pick up a couple of places where their orbits are closer together, where they're a little bit brighter on the screen. Out here beyond Neptune is a region that we call the Kuiper Belt, and that's really going to be the topic of next week's show, so I won't get into it too much. If we work our way into the inner solar system, we've got those objects that cross the orbits of the gas giants. I already said their name once. They are centaurs. Then we've got inside Jupiter's orbit. Those are the ones that we really think of as asteroids today. And then there are the Trojan asteroids that lead and follow Jupiter around in their orbit around the sun. And other planets have Trojan asteroids as well. You can find some with Uranus, Neptune, even Mars, and Earth has one as well. And since we can break these objects into all these different categories, categorizing an important part of science, there's also a label that applies to all of them. We call all of these small worlds collectively minor planets. So it is the IAU Minor Planet Center that keeps track of all of them. All right, excuse me for one moment there. So it's those 1 million minor planets that we know of in the solar system, and so we'll kind of break this up into a couple of shows. We'll deal with the ones outside of Neptune's orbit next week. Since this is a good pause point, we've got a couple of questions that have come in. Let's see. Shannon, why don't asteroids start orbiting the Earth when they get close? Well, Shannon, don't read ahead. Are they going too fast to get caught? Who says they can't get caught? Lauren asks, how do they know if an asteroid has already been discovered? Well, it's the IAU Minor Planet Center that collects all of the observations from astronomers all around the world, and they're publicly available. You can look into them too. It's minorplanetcenter.net, I believe. Just go there. You can find the observations of all of the astronomers from all around the world. They are freely available, so anybody can access them. If new observations are reported and they match something that's already in the database, the Minor Planet Center computers will line that up and just add those new observations to the record for the old already known asteroid. So yeah, it's pretty tough. It's a big job to keep track of all of those objects. And surely among a million plus objects, there's some interesting stories to tell, like the one that Shannon hinted at. So Shannon, let's address your question immediately. I like to bring some of these interesting examples to you in part of an ongoing series that you may have seen in the Dome in the past. I call it Better Know an Asteroid. And here are some recent examples. If we zoom in on the Earth here, we can track down a recently discovered asteroid turned up in images taken back on February 14th, Valentine's Day of this year. So it has the designation 2020 CD3. 2020 CD3, pretty interesting because it was spotted pretty close to the Earth. I'm going to run time backwards here because it's gotten a little farther away today, and hopefully CD3 will make an appearance on our screen. Here it comes, a kind of yellowish dot with a red line behind it. So it was spotted relatively close to the Earth, and because everything in the solar system is just following the laws of physics, you can look backwards in time from where it was spotted on Valentine's Day and found that it had gotten close enough to the Earth, but it was moving slowly enough at the time that it must have been captured by Earth's gravity. It was bound to the Earth gravitationally. So this asteroid was in orbit around the Earth. It made some headlines a couple of months ago because it was kind of like a second moon of the Earth. Of course, astronomers have a complicated name for it. It was a temporarily captured object. The orbit of 2020 CD3 got far enough away from the Earth, several times farther away than our own moon, our permanent moon, usually travels. And at its most distant points, its apogees, the sun's gravity affected it quite a bit, and so there's a little bit of uncertainty in where it was moving in its orbit around the Earth. We think it was probably in orbit around the Earth for a couple of years. So for the last couple of years, in a sense, the Earth had two moons. At least. We've detected a few other temporarily captured asteroids like this in the past, and because most of them are pretty small, CD3 here was about the size of a car, they have to be pretty close to the Earth for us to actually be able to see them. So there may be captured asteroids that are a bit farther away that we just don't know about. And we've certainly caught a couple of other captured asteroids in images in the past. So at least for a while, Earth had two moons. CD3 here has escaped now. It's back in orbit around the sun. But that's not an unusual thing. And you have to get pretty close to be captured by the Earth's gravity because it's not terribly strong. But we saw the orbits of a lot of strange outer moons around the gas giants last week. And the thinking is that a lot of those distant moons around the gas giants started their existence as asteroids or comets in the solar system and were captured by those other planets. So you can certainly transition from asteroid to moon, and in the case of CD3, back again without too much difficulty. So kind of interesting that things can jump from one category to another. Let's talk about another object that perhaps should be reclassified by astronomers. Let's zoom out so we can see the main asteroid belt again and give you an update on the asteroid Hygiea. Now this is an old one. It's been on the books since 1849. It was just the 10th asteroid discovered. Astronomers were able to see it so long ago, even though it's in the main asteroid belt, kind of far away, because it's fairly large. We now think it is the fourth largest object in the asteroid belt. For comparison, here are the sizes of the four largest objects in the asteroid belt, centered over Richmond. We got Ceres, Vesta, and Pallas are next. They're virtual twins. And then we think Hygiea is number 4 in the size ranking there. But not a lot is known about it, just because it's relatively far away compared to those other big asteroids. So we didn't have any great views of Hygeia's surface until recently. And there's a new camera called Sphere on the Very Large Telescope, the European Southern Observatory. And this is a real picture from that telescope of Hygiea. Now, it's not crystal clear, but to help you pick out patterns in that image, here's a comparison with Vesta, a real sphere image on the left, a model of what it should look like using data from the Dawn spacecraft, which visited Vesta a few years ago. So even though this picture isn't crystal clear, not really high definition, you can pick out big craters and things like that. With a couple of pictures, you can also work out the overall shape of this asteroid. And this is what astronomers think the shape of Hygiea is. If we compare it to a perfectly spherical object, that's the blue thing, you can see that's pretty close. Now, the IAU has some other rules, and these other rules tell us how we should classify minor planets and dwarf planets, right? That's another group. So dwarf planets are supposed to be in crowded parts of the solar system. Here is not the entire group of asteroids in the asteroid belt, but a group of asteroids we call the Hygiea family, because we think they have very similar orbits to Hygiea and may have broken off of Hygiea in a giant collision. If there were a giant collision that flung a bunch of debris off of Hygiea and made this family of smaller asteroids, perhaps the impact also nearly vaporized the original Hygiea. If it were molten, if it were more like a liquid, gravity could have more easily formed it into a nice round shape. And then perhaps it reached what we call in science hydrostatic equilibrium. You just may know that as round. And if it is a round object in a crowded part of the solar system like the asteroid belt, technically, maybe Hygiea is a dwarf planet rather than simply an asteroid. That is the category that Ceres finds itself in today. It's big enough to be rounded by gravity, and so it is a dwarf planet as well. All right. Speaking of objects that should again maybe be reclassified or maybe moving between categories the IAU uses, let's add another object to our scene here. This one goes by the designation P 2019 LD2. Most of that probably makes sense to you if you caught the bit about designations at the beginning of the show. The letter P might be a little bit mysterious, though, and let me see if I can explain that. This is the orbit, the green one, that LD2 was discovered on late last year. Now, it kind of looks like the orbits of the Trojan asteroids, but it's not a perfect match. And in this real picture of LD2, you might just be able to make out kind of a fuzzy tail stretching away from it. So for that reason, it kind of looks like a comet. Now, this isn't unheard of for asteroids. We sometimes call them active asteroids. But something else might be going on here with this particular possibly asteroid. If we, again, just use the laws of physics to look forward in time, we can see that in the next couple of years and then over the next few decades, this object is going to suffer multiple interactions with Jupiter, and Jupiter is actually going to shrink its orbit so that 2019 LD2 comes more and more into the inner solar system. If it starts behaving more and more like a comet as it gets closer to the sun, then we'd expect it to, be designated as a comet. And so now that letter P out front tells us that astronomers actually think that, although they called it an asteroid at first, this is a periodic comet. It would become part of the Jupiter family of comets. But let's see, could we perhaps decode this story a little bit more? What if we go back to the present day? And instead of looking forward decades, centuries at a time, what if we looked backwards in time instead? If we do that, then according to the laws of gravity, a few years ago, LD2 flew by Jupiter at relatively close range. That interaction shrunk its orbit to give us what we see today. But decades ago, the orbit of this object would have crossed the orbit of Saturn as well. And then it might truly have been part of that population I mentioned earlier, the centaurs. They get that name because, in mythology, centaurs are half horse, half human, right? So in astronomy, a centaur is kind of half asteroid, half comet. They have properties of both. It's kind of a hybrid category. So here we have an object that, if we had found it a couple of decades ago, probably would have just thrown it in the Centaur bin. Because of where it was discovered, astronomers thought for a moment it was an asteroid, maybe one of those Trojan asteroids. But now with further study, we see that perhaps its true identity is a comet that is just making its first journey into the inner solar system. So I think some of those transitions are pretty interesting as well. But there's been perhaps no more interesting asteroid story in the last couple of years than the one that started in October of 2017, when an object called Oumuamua was found relatively close to the Earth. So at first glance, perhaps just a near-Earth asteroid, but if you look at its path through the solar system, the speed at which it was moving, you can see that it's moving too fast to be bound by the sun's gravity. So it can't be part of our solar system, or at least it must not have formed here. So the most likely explanation is that Oumuamua formed somewhere else and just happened to fly through our solar system. It was categorized as an interstellar object or even an interstellar asteroid for that reason. If we fast forward from its discovery location between the orbits of Earth and Mars to the present day, we can see that in just over 3 years, or almost 3 years, it has flown almost 2 billion miles to get out near the orbit of Uranus. I mean, that's faster than even our spacecraft that are escaping the solar system. So this might be some kind of alien asteroid that formed around some other star. Or, in a theory published just last week, it could be something even stranger. Astronomers now suspect that its odd shape, as well as its unusual speed as it left the solar system, it was actually going a bit faster than just simple gravity would explain, suggests that this may be something like a hydrogen iceberg, a huge chunk of molecular hydrogen ice. Now, these wouldn't form like asteroids or comets. These would have to form in huge clouds of dust and gas, where the kinds of nebulas where new stars are born. Now, we've never detected one of these directly, and there's no direct evidence that Oumuamua was one of those hydrogen icebergs. Perhaps the best way to answer that question would be to visit it up close, but it's too far away now. It's moving too fast. We'll never catch up with it. The European Space Agency is working on a mission that would kind of park a spacecraft in orbit, ready to chase down one of these future interstellar objects if we do identify more. But that's years down the road. So for now, we are exploring other asteroids in our own solar system, and we've got 2 missions that are actively exploring asteroids in our solar system, and I'll try to get the labels up right for you. In the meantime, I'll read them on your behalf. They are the Hayabusa 2 mission, which has completed its exploration of an asteroid named Ryugu. It's on its way back to the Earth with a sample of that asteroid. And then we have the OSIRIS-REx mission, which is studying an asteroid named Bennu. Now, both of these missions are interesting, and they're both revealing unique details about their targets. Here are our best observations of these asteroids to date. These are the shapes of the asteroids and their relative sizes. That's Ryugu on the left, the Empire State Building for scale, and Bennu on the right. So they've got similar shapes. They also have similar orbits around the sun, and now astronomers think that they may possibly have been formed out of the same giant collision, kind of like we saw with Hygiea. We think that collisions have happened among asteroids in the past. Space is really big. The asteroids are mostly pretty spread out, but given 4.5 billion years, some are destined to collide eventually. And there's going to be some debris left behind. And both these asteroids really look like sort of rubble piles that would have been built up from smaller rocks from one of these collisions. The similar makeups of these 2 asteroids may point to their source being the same giant collision. That's another brand new published theory. Now, let's take a closer look at these asteroids real quickly, showing you some real images of Ryugu from the Hayabusa 2 mission on the left. Now, this is a mission of the Japanese Space Exploration Agency, and they had some pretty unique ideas about exploring the asteroid. Not only did they send the spacecraft to take pictures and collect a sample, they also took some landers with them. The first to be deployed were 2 small ones called the Minerva landers. These twin landers descended to the surface, snapped these real pictures that you're seeing there, and one of them even had a little flywheel inside that allowed them to hop around. They were also solar powered, so they were able to take observations for a number of months. Then later, the larger mascot lander was deployed. This one had some different instruments on it, still able to take images, which you can see, although my picture's in the way of one of them. And the mascot lander actually resulted in perhaps my favorite picture from the entire Hayabusa 2 mission. We have real images from Hayabusa 2. You got the asteroid Ryugu in the background, and then the real mascot lander descending to the surface of the asteroid. I think that's pretty cool. Then, of course, we've got actually collecting a sample of the asteroid. Now, both of these missions have chosen to take different approaches here. For the Japanese Space Exploration Agency, they descended to the surface of the asteroid. The Hayabusa 2 spacecraft, you see a bit of that sticking out in this video, actually fired a projectile into the asteroid, churned up some material, as you can see, and the hope is that they collected some of it in the little sampling horn, the device you see sticking out in the camera view there. So they took that first sample. That's the first sample collection attempt, and then later on they collected a second sample, but to mix things up a little bit, they deployed another little device. It was called the Small Carry-On Impactor, which just means well, they had an explosive device that opened up a crater on the surface of the asteroid. They collected another sample there, and they hope to collect subsurface, underground material in that sample, which might give some more hints about how the asteroid formed. So that sample is on its way back to Earth. The Hayabusa 2 spacecraft has departed Ryugu, should return to the Earth in December. The OSIRIS-REx mission, on the other hand, still ongoing, still at asteroid Bennu. Zooming in here to show you just how amazing some of the images are. This is a real map of the asteroid, and in fact the OSIRIS-REx mission has mapped Bennu at a higher resolution than any other world in the solar system has been mapped. Even the Earth. There are parts of the Earth that we don't know at the level of detail that we do all of Bennu. We can see down to the smallest pebbles on the surface of Bennu, which is pretty important because when OSIRIS-REx collects its sample, you can see some images from one of their rehearsals on the left there. They too are going to touch the asteroid. For the OSIRIS-REx mission, they'll just shoot some nitrogen gas at the asteroid to churn up material and catch it in their sample collection device, and then return that sample to Earth. Brand new breaking image for you. Just yesterday, they released images from a close pass of their backup sample site. This probably isn't where they're going to collect their real sample, but I think this is the highest resolution image they have released. It's actually a combination of over 300 individual pictures, and we're just going to zoom in real quick before the end of the show because the scale of the image is amazing. For any technical experts in the audience, the resolution of the picture is 5 millimeters per pixel, about 0.2 of an inch per pixel, and a little black dot that I've added, circled in green. That was 4 pixels wide. That's the size of the rocks they're going to try and pick up when they collect their sample. So we're seeing down to the scale of the rocks, the individual pieces of this asteroid that they hope to collect. So those are the ongoing missions of exploration in our solar system. More coming up in the future. We got the Lucy mission headed to fly by several of Jupiter's Trojan asteroids. We have the Psyche mission destined for an asteroid with the same name that we think is composed mostly of metal. It might be the core of an ancient planetoid that had the rocky outer layers stripped away. And many more missions coming up. We want to study some of these asteroids like Bennu and Ryugu because these are typical near-Earth asteroids like the ones if they did hit the Earth. It's pretty important to know what kind of asteroids might hit our planet. So if they really are going to be rubble piles like Ryugu and Bennu, we want to know about that. On a related note, Shannon asked, when was the last time an asteroid hit the Earth? I don't know off the top of my head, but little tiny rocks run into the Earth all the time. If you see shooting stars at night, those are just little bits of rock and dust in the solar system. Sometimes there are larger ones. You might hear them called fireballs or bolides. Those, may be larger meteoroids or if you like, very, very small asteroids. I don't remember off the top of my head the last time a sizable asteroid, maybe something a few yards, a few meters, size of a car, hit the Earth, but it's fairly common. These real small ones, they're going to burn up mostly in the atmosphere, and if it's over the ocean, we may not know about it at all. Of course, there have been big impacts as well. You've got things like Meteor Crater in Arizona. That's a not so ancient impact, and the most headline-grabbing asteroid impact, certainly 65 million years ago, circling all the way back to the dinosaur mentioned at the beginning of the show. So there you go, a quick look, kind of, at asteroids in our solar system. Got a slightly more accurate map of the solar system on the screen for you. Added those hundreds of thousands, nearly 1 million asteroids, minor planets of all types to our solar system. Next week, if able to join us again, we're going to head out beyond the orbit of Neptune and check out the minor planets out there, primarily the Kuiper Belt, but we'll talk about Pluto and some of its other dwarf planet neighbors, and maybe even the idea of another large planet in the outer solar system. So that's all on tap for us next week. Again, Thursday afternoons, 2 p.m. Hope you can join us again, and these long shows are becoming a pattern. Better pack some snacks for our next journey. So again, I'm Justin, happy to take you through the universe. Until I see you next week, take care and have a nice day.